Yes, great. So I just want to introduce Ulf. So we are, we are all interested in, of course, what could be beyond black holes, right? And so Ulf and the collaborators are, well, he's going to tell us about his work on things that might be not black holes, but still look like black holes very much. And I like to think of them a little bit as alternatives to what we typically think of as fuzzballs. So yeah, so thank you. Go ahead.
Okay, yeah, thank you very much. It's great to be here and get this opportunity to talk a little bit about this work, which goes back a few years, but we have been continuing to look at this idea. And sort of the main message you see in this picture here of a real black hole, but then in the darkness, it's replaced by something else, something which is sitting outside the horizon, sort of cuts off the space-time, so there is no horizon, but there is something else there instead, which is mimicking quite successfully what otherwise would have been a black hole. So let me then just list a few of the key papers. Can you see this? Did it work? You see the list?
Yes.
Yeah, okay, good. So the first paper was in 17, where we introduced the idea. And we had another idea. So it was me, Giuseppe Di Bettetto, and Sevendra Giri, and I and Sevendra, we made a follow-up when we looked at rotating black holes or black shells. And we recently updated that work with some further calculations. And then quite recently, the date is wrong, it should be 2109. It's by Franz Pretorius and Louis Lerner and me, and we actually did some numerical work to test the idea, which actually worked out quite successfully, and we also learned a few new things about the model. And then I will also tell you a little bit about another development, much more recent, together with Vincent van Hemmelrijk and Thomas van Riet. I will not have that much time to tell you about that, but maybe towards the end. Okay, so the outline is that I will give you some brief motivation. I will describe the basic idea behind the shells. I will discuss the problem of stability, which is one of the conceptually most challenging parts. I will then discuss rotating shells, which is mathematically the most challenging part, and then discuss towards the end, as I said, a little bit about charged or even supercharged shells, and then some outlook towards the end, where I'll discuss what I think needs to be done to further test these ideas. Okay, so the motivation is that we have the black hole information puzzle, and to solve it, you really need two different things. You need a way to store information so that it's available to the Hawking radiation, so that the unitarity of quantum mechanics can be retained. I mean, if you believe that that is a requirement of a fundamental theory. Now, this is something which is naturally solved by string theory in some sense, and there are many impressive calculations where you, using brains and extra dimensions, can get exactly the right number of degrees of freedom to get the entropy and everything to work out and coincide with what you get from Hawking's results. Still, it's a mystery how to explain how you can at the same time fall inside of a black hole if the information is available for an asymptotic observer looking at the Hawking radiation. And here, of course, this is sort of claimed to be taken care of by black hole complementarity, where the two pictures are supposed to make some kind of sense anyway. But I would say that even though the counting of number of degrees of freedom and entropy is something that seems to be solved by string theory in some sense, the total picture of space-time is something which is much less understood. And in fact, there has been arguments over recent years with respect to firewalls and fuzzballs and so on, that in fact, it's not clear whether there can be or should be even an horizon. Maybe the black hole information paradox problem is so severe that a consistent theory of quantum gravity cannot really retain a horizon. So, and this is sort of the motivation for what we did. that we wanted to see if there was a simple way, inspired by string theory, to construct an object which could replace a black hole. And the idea that we have been pursuing is the idea that black holes are replaced by black shells. So we assume, without really, and this is of course something that we need to come back to, but we assume that the space-time is actually unstable against decay to true vacuum that could be ADS. We are living in a metastable vacuum with a very, very low probability can decay to a true vacuum ADS. So our Minkowski, or actually slightly the de Sitter space-time, is unstable, but we need not worry about that because it will take billions and billions and billions of years before this disastrous decay actually happens. But what if a cloud of matter is now collapsing, threatening to form a black hole? Well, then the idea is that there is an increase in entropy if a bubble of ADS nucleates, expands, and captures the infalling matter. So the nucleation is triggered by the collapse of matter. And the idea is that matter is stuck to the shell in the form of a low temperature gas, and we'll come back to that. It has a huge number of degrees of freedom, and there is enormous enhancement of the probability of nucleation when ordinary matter can convert to this matter stuck to the shell. And that means then that the nucleation of this true vacuum, rather than having a very, very low probability, it will be inevitable if matter is collapsing, threatening to form a black hole. That's sort of the basic idea. And I know that the same idea has been discussed in the context of fuzzballs as well. So that's sort of the idea. Matter is threatening to form a black hole, but before that happens, this bubble is formed and it's contained in a shell, a brane, which marks the boundary between ADS and the surrounding space-time. Now, in order for the shell to be static, it has to solve the junction conditions across the shell. And these are the junction conditions then, where the pressure and the density and the pressure corresponds to the density and pressure of this thin shell, which is sitting there between the surrounding space-time and the ADS. And you see here how the extrinsic metrics, which are used here, the metric gives an extrinsic curvature, and you see here the Schwarzschild space-time on the outside, and you see the ADS space-time on the inside, where K represents the ADS scale. Now, this is typically the kind of setups that you have for gravastars. Often gravastars have a positive cosmological constant on the inside, while we have a negative. But they all share a very undesirable property, and that is that even if you design energy and pressure such that you solve the junction conditions, this will be unstable. And the shell will either start to expand or contract. It's a bit similar, actually, to the Einstein's unstable universe. And actually, the mechanism is sort of the same, but one dimension down. So this is something which sort of the gravastar models typically suffer from. But as you will see, we have an idea of how to solve this. Now, in order to further understand how to design this shell, because this is really a matter of trying to come up with something which sort of conceptually, heuristically can do what we want, it's useful to write the junction condition in the following way, so that you have actually an energy of matter which is on top of the piece of the junction condition that would be there if you only had an empty surrounding space-time and an ADS bubble. So we are focusing on that excess energy that we call E. Now, that excess energy, on the other hand, we could also associate with an infalling shell of matter, a shell of ordinary matter, which is then separating a Schwarzschild space-time from a Minkowski space-time on the inside. So that's the junction condition that you see on the bottom, with E equal to R minus R square root of 1 minus 2m over R. Now, that junction condition can also be understood as simply the total mass energy of the system corrected with the gravitational binding energy. So the asymptotic mass is m. The local energy measured at some radius r is E, but then of course you also have the gravitational binding energy. So we are focusing on this E here as being the locally measured energy, but then that means that you have the asymptotic mass, and then you have also, of course, taken into account the gravitational binding energy. And we now try to see if there is something happening, something special happening at some particular radius. And then as you see, if we now, instead of this E, is considering the corresponding energy density, then you have it here. We have simply divided by 4 pi r squared. And then you can also calculate the corresponding pressure by using the standard relation of pressure between pressure and energy now in 2+1 dimensions. And then you see that at a particular radius, which is outside of the horizon, the Buchdahl radius, then we find the equation of state of radiation. The Buchdahl radius appeared very early on in the history of general relativity, and it typically associated to the smallest radius that you can imagine with some kind of sensible energy equation of state. You could have a kind of stable object. It's already in the paper by Schwarzschild, and Buchdahl proved that if you have an energy density which is increasing towards the center, this is the smallest radius object can have. So this radius have already shown up in the early history of general relativity, and now we see that it corresponds to a very particular radius where infalling matter requires a kind of a shell with a particular equation of state in order for it to be captured. So the idea then is that if we have a shell, a nucleated bubble with a shell which captures infalling matter, it's very natural for that to happen at this radius if you demand for some reason that matter should easily be converted into radiation on top of the shell. This is a very heuristic argument, and you can poke holes in it, but this is sort of the way we are trying to move forward in order to intuitively build up something that makes sense. So we pick this radius to be the nucleation radius, and we imagine at the shell, which is tunneling and nucleating at that radius, captures the infalling matter, and that infalling matter becomes radiation stuck on the shell. Okay, so that's sort of the pictures to have in the back of our minds. Now, what is the stringy construction of the shell? Well, certainly you can in 4D construct supersymmetric black holes by wrapping branes along cycles in compact dimensions, let's say in type 2a and more particularly in type 2b. And you can imagine now a bubble, which is then you can have, I mean, you can start out with the 3 branes which are wrapped around the extra dimensions, and they would be like points in 4D. But let's imagine now that we have the phenomenon of a brane polarizing from a D3 into a D5, and it puffs up inside, not of the extra dimensions, but in 4D. So now we have the kind of structure that we would like to see. Now, furthermore, we can imagine that inside of this 5 brane, there is furthermore D3 branes and even anti-D3 branes which are dissolved into this 5 brane. The action of this brane, now looking at it from the point of view of 4D, would be as you see the action here, you have the determinant of the metric, but you also have these dissolved lower dimensional branes, which then will be the zero branes from the point of view of 4D, that would correspond to a flux, which is carried by this brane. And we find a particular energy density then on top of the brane, where n is then the number of dissolved zero branes or pairs that would be fluxes and anti-fluxes. And that would correspond to a particular energy density that would go like 1 over r to the 4th. And that would correspond now in our 2+1 dimensional brane theory to a stiff gas with pressure equal to the density. So hereby being motivated from the stringy idea of a brane puffing up from 3 to 5, or from a 2 brane to a 0 brane to a 2 brane, if you look at it from the point of view of 4D, we are naturally led to these two ingredients of a brane with a tension and also this stiff gas of this dissolved zero brane on top of the shell. Now, the point of this now is that this stiff gas, that will be subleading, but as you will see, it will be important in order to keep track of the number of degrees of freedom of the radiation which is stuck to the brane, which will be much more important. So these are the ingredients that we have. We have a brane with a tension, we have radiation stuck to the brane, and we have a subleading stiff gas. Let me now make a little more detailed calculation in a moment of how these things relate to each other. But first, let us look at the junction conditions. And we assume now that the ADS scale is microscopic. So K is a very, very high energy, maybe close to the Planck scale, string scale, whatever. And then we expand the junction conditions for large KR. So we have some set of energy, which you see here on the left, which are the things which are carried by the brane. And then we have the extrinsic curvature, so the difference in the extrinsic curvature expanded to lowest few orders on the right-hand side. And here we have the rho B and the PB, which I defined before. Now, you can naturally solve the junction conditions by demanding that at the stability point, the tension should be what you see here, the energy density and the amount of stiff gas should be of this sort. You could imagine solving these conditions in many other ways, but this is the unique solution if we assume that all the explicit mass dependence only sits in the row, is in row B, actually. So it only happens to be here and nowhere else. Always, here we have a dependence on R, but the dependence on the actual mass, explicit mass of the system is only sitting here. So it should have been B there. So this is just an arbitrary choice in some sense, but it's very natural. And as you see, it leads to interesting consequences. Okay, now let's coming back to these various ingredients and their different roles. So first, the tension of a DP brane. Well, then you have to wrap the extra dimensions, and we obtain then a 2 brane in 4D. And we assume that the extra dimensions have a certain size L. It's the D brane. So here you have the tension, effective tension of the brane. So that should go into the calculation. The Planck length is, of course, again, obtained through looking at the compactification of the extra 6 dimensions. And we can now solve the junction conditions to leading order. And then we find, of course, a simple expression for tau. It will just be this. Tau should be basically just given by the K. And here, using these relations, you find then, assuming the junction conditions to be solved, that the ADS scale needs to be this in terms of the fundamental parameters that we have, given now that the tension of the brane is provided by this wrapped high dimensional brane. Furthermore, We have the junction condition for the stiff gas, where we then identify these subleading terms. And this allows us to obtain an expression for n, the number of degrees of freedom. And then we see, and this is a very nice feature of the construction, that if we have a fibrane, so it's a wrapped three brane polarized into a fibrane, we find that the number n, which is really the number of the zero branes dissolved, it simply becomes r, the radius of the shell, divided by the Planck length. Everything else is canceling out. And you can also see...
What do you mean by zero branes? I mean, when
Yes.
you have a five brane and a three brane, what do you mean by zero brane?
No,
Because
I'm saying like this.
so-
Sorry, that's just by thinking about the dimensional reduction. So in reality, we have a three brane wrapped along the extra dimension, which looks like a zero brane from the point of view of 4D,
Okay.
in the dimensional reduction. And the same, the five brane looks like a two brane in 4D. So that's really the shell itself.
Mhm.
Now, as it turns out, that if you go through T and S dualities, you can actually see that this structure remains. So this n equal to r over LP, it's invariant under stringy dualities. So you could imagine other dimensions of the wrapping of the branes, then you could have an S5 or an S5 or D5, doesn't matter, you get the same result. And in our first paper, we're actually looking at some detailed examples where we had several different kinds of branes which were contributing. We had an attempt there to, in some sense, embed everything into a reasonable string model. But this is a very generic result, which is extremely good, because then you see that the number of open strings which are going between the dissolved branes will now be n squared, and that's just proportional to the number of degrees of freedom of a black hole. So if radiation is supported by the dissolved zero branes, which are the wrapped three branes, we naturally get that the energy density, that should be n squared t cubed, actually fits in such a way that it can carry essentially the mass of the collapsing object, and we find a temperature that will be of the order of the Hawking temperature. So everything works out. It's a kind of a non-trivial construction here with these three ingredients, and we need to have this n to come out right, but it does if we consider this stringy construction. Now, what about the temperature? Why should the gas have this particular temperature? Well, clearly, this shell now, if it's static, it's actually locally accelerating. There is a local en-route temperature that it should be heated up with. And that's our assumption here. I mean, note, of course, that the en-route temperature is something that you can even use to calculate the temperature of a black hole. You imagine, in fact, the shell again, which is heated to the local en-route temperature, and then you slowly take the limit where the shell is approaching the horizon. It gets hotter and hotter and hotter, but there is a redshift if you're looking at it from far away, and in that way you can obtain the Hawking temperature. Here the temperature will be slightly different because we are not taking the limit, whereas having a shell which is sitting at a finite distance out at the Buchdahl radius, so it will be very, very cold and further redshifted a little bit when you look from it asymptotically. So the actual temperature of the shell for an observer who is looking at it from far away will be a little bit colder than a black hole. And in fact, it's a very, very cold shell, but it has an enormous number of degrees of freedom, of course. And the entropy will be of roughly the same order as the entropy. Well, it will be of the same order as the entropy of black hole, but not quite. There are some numerical factors which differ since this shell is sitting a bit outside. Now, I think before going into talking about stability, just a conceptual point here. Sometimes it's argued that alternative to black holes need to be very, very close to the horizon in order for not to come into conflict with observation. You think that something which is falling in and then stuff should be reflected outwards. You should see something. There should be an echo or some sort. That is not true for this model, because this is supposed to be perfectly absorptive. I mean, it's really perfectly absorbing object here, because it has so many degrees of freedom. So anything that you drop down on the surface, that's sort of our idea, is that even though the redshift is finite, it will be dissolved into the degrees of freedom of the shell, simply because there is the huge entropically favorable for the matter to get stuck there. Still, of course, it has a temperature, so it will very, very slowly evaporate, more or less in the same way as a black hole will do. But whatever is going in there will not come out, not because it's swallowed by the horizon, but because it gets stuck to the surface of the shell. Now, all of this might sound, okay, sort of reasonable, but the big problem is, of course, stability, because why would this be stable? In fact, it's not. You can easily see that if this is the full story, this would never work, because this critical point is an unstable critical point.
May I ask a question?
Yes, sure.
What's the width of the shell?
Here we are assuming that it's infinitely thin. So we are thinking of a fundamental brane coming from string theory, let's say.
So it violates all the entropy bounds.
Violates all the entropy bounds in
Yes,
what
because
sense?
it has a black hole worth of entropy and a volume that is much smaller.
No, it's not. I mean, it's a fundamental brane of string theory. I mean,
Yes.
I mean, it's just a brane with a tension. There's nothing which would.
No,
it
but
doesn't violate anything.
you said that it has an entropy that is similar to.
No, not the brane itself.
Yes,
but the brane is carrying a gas on top of it.
Yes. So, but the whole system has an entropy of a black hole, and I was asking about the width of the brane together with whatever is carrying.
But this is a codimension 1 brane, so there's nothing. It doesn't violate anything.
Well, the entropy bounds typically say that the maximum entropy is the entropy of a black hole of the same volume, right?
I don't really understand. I mean, I mean, furthermore, I mean, the gas is no. I don't understand
I think what Rami wants, maybe I'm understanding correctly. I mean, so normally, again, if you put a surface around the object, the entropy inside the surface should be bigger than should be smaller than the entropy of the black hole. But
I think it is.
That it is. But I think what Rami wants to do, he wants to put the surface both on the outside of your object and on the inside of your object, inside the ADS part. And then he wants to compute the area of that surface and to ask, because then I think it's a lower.
I'm not sure. I mean, something which might complicate that reasoning would be that the fact that, I mean, the thermal wavelength is of course larger. I mean, as big as the shell itself.
Can you do that thought experiment that you used to argue for this entropy bound for this case? The situation is different. You cannot really fall down a shell of matter to argue for this entropy bound, right? The situation is different, so I think it's not applicable.
Okay, I need to think about it more, but
if the width, as you say, of the gas is comparable to the size of the shell, then it might work, because in this case the actual volume is much larger. But okay, it's something to think about.
I think so too, because there could also be something which I confess that we have been thinking a little bit about, it's whether there are some finite size effects here, because the thermal wavelength of the gas is compatible to sort of the area of the shell. So there could be things here which we have not under control. So I think that this is something to think about. Absolutely.
Can I ask a slightly orthogonal question? You made the assertion that this brane was purely absorptive, but different species of branes don't like to interact with certain other branes. So one class of brane can't end on an NS5 brane. So So if I drop the wrong kind of probe in there, surely it will be repelled or won't want to attach to this thing. So I don't know that this thing can be made perfectly absorptive with the model you've got. There will be things that won't want to attach to it.
Yeah, I think that I mean, the sort of picture we have of it is that you have a basic brain which sits there, which is the puffed up D5 brain, which is carrying the tension. But then on top of that, it's brain anti-brain systems. And so it's supposed to be uncharged. But I think that what you're saying then, dropping a brain into it, it should presumably be something that would look charged then maybe from.
Yeah, I just think if you try to lower one class of brain that doesn't want to enter into a D5 brain, then it will just it'll.
I mean, you could imagine that if you have a brain which if you have a charged black hole with a particular brain which is carrying some extra charge, and then you drop something into it which have the same charge, that would certainly not have would like to. That would be repelled. So I'm not sure. I mean, you have a good point, but then you have to think about what it actually corresponds to from the point of view of 4D.
Yeah. I had actually a question related to Rami. So when one's trying to figure out what the transverse size of this thing is, what temperature of the gas on the brains is one supposed to use?
I mean, the temperature that we have been using by assumption is the local Unruh temperature.
But you were talking about like the thermal wavelength being the size of the black hole. That sounds like the temperature is measured.
No, but that's what you get, because the local Unruh temperature, since we're sitting at the radius, which is of order 1 bigger than the horizon scale.
Okay.
The only scale in the system is really 1/r.
When you say order 1, you mean in units?
It's the Buchdahl radius, so it's 9 times the. So it's just numerical factors. That means that the temperature, locally measured temperature, will be of the order of the Hawking temperature.
Okay, but you have n squared of these things, right?
You have n squared of these things, yes.
So if I just did some very crude estimate of a gas of that on a D3 brain, what would be the transverse size of the brain? Because I've got scale among those excitations on the brain. There are some scalars which are puffing up some transverse width because you've thermally excited those scalars.
Yeah, that I don't know.
Okay. So, but that would definitely contribute to the width of this thing.
Yeah. But that I know. It could in fact be that we are looking at some kind of average now, and that it could be sort of fluctuations given some width. Absolutely.
Yeah, some scale of order R.
Yeah.
Okay.
So, but so it's a very classical picture that we are trying to see where it leads. But of course, it could be important corrections.
So at the Buchdahl radius, you have this thing, and then under your assumptions, then the inside is some ADS inside that radius of what characteristic radius of curvature?
The characteristic radius of curvature that we have assumed is that it's really high energy, microscopic, close to string or Planck scale. And that is in order for the energy difference between the outside and the inside be such that it can be matched by a brain of a fundamental attention set by some fundamental scale. So we assume it's sort of high energy scales. So it's a very fine-tuned system in that sense. So that the tension is such that it, in the junction conditions, separates between the outside and which have no cosmological constants essentially, and a big negative cosmological constant on the inside, but everything is fundamental string scales.
So a probe, if the probe wasn't, if the string coupling was low enough that something would sort of like naturally pass through these D brains as a first approximation, it would see some extremely high tidal stress as it tries to pass through this shell?
Absolutely, yes.
Yeah,
yes.
okay.
The idea here then is that it would be very difficult for almost anything to pass through, because it would be entropically so much more
It would be
favorable.
tidally disrupted in some strong way. Yeah,
Yeah.
okay.
Okay, now, so unfortunately, the generic problem now is that it's unstable, and the extra ingredient that we have introduced then is that there is an energy transfer between the brane tension and the gas. So actually, even though we haven't been able to model that in detail, the tension can be varied. So we assume that there is a tachyonic mode, which might be stabilized by the temperature or something. We have not been able to model this in a good way. But the idea is that there can be energy transfer between the gas and the tension. So the tension can reduce itself, and the energy can be transferred into the energy of the gas. So the gas energy density of the gas increases, and it can go back and forth. So we have introduced such an extra source term, as you see here, in the equations of, well, in the continuity equations for these two components. And then we have furthermore assumed that the source term, it can be sensitive to temperature change and to a change in area. So is F here is actually as the area of it's something that you can also imagine being sensitive to a local change in the area of the shell. So these two ways for the source terms to sense what's going on, we are now parameterizing by these two arbitrary coefficients, alpha and beta. So we put this source term into the game, and then we see for which values of alpha and beta can we cook up something which makes the shell respond in such a way that it's stable, but also that if there is a further shell of matter which is being collected by the shell, that it relaxes back to the new and larger radius of the shell, so that it can absorb matter and then grow. And then I will not be able to go into the details here. All of this is in the paper together with Pretorius and Lehner. The stability of the linear analysis requires that these coefficients alpha and beta satisfy these constraints. And we also, of course, want the shell to relax to the new Buchdahl radius. And that means that there is a further constraint of alpha and beta. So it's just one parameter left actually here. Okay, now it turns out that you can actually solve these equations numerically, and that's for a spherical configuration. You can also actually turn on the whole machinery of relativistic hydrodynamics and also include transport coefficients so that you introduce viscosity. And that means that any oscillations will actually be damped. And if you do that, and this is, I make a very, well, rather long story short, and you have the details in the paper here, then you can see that actually it sort of works. So you see here, and here you should in particular look at case B here. So then you see how the shell starts out at the Buchdahl radius. We have a black shell there from the start. Another thin shell of ordinary matter is falling in, and it gets captured by the shell, which of course gets contracted. It's contracted, but then it starts to grow again towards the new Buchdahl radius. Now, in this case, we have actually hit it again. Before it had reached this stable point, we hit it again just to see what it happens. So it contracts one more time. And then we let it be, and we see then how it relaxes back to the correct radius. So this 0 is that just shows that you have no deviation from the expected radius. So this line here with these two contractions, these two hits and contractions and re-expansions correspond to a shell which is hit and then it's contracted together, but then start to grow again, and it hits again, and then it relaxes back out to the expected radius. So what we have here is actually a system with the capacity of mimicking a black hole. So just to summarize again, we have three components. We have a tension, we have a gas of radiation, and we have this stiff gas, which is determining the number of degrees of freedom. We had to add to the system a source term, which is transferring energy between tension and gas. You could sort of heuristically say that that means that the tension can respond. There is some tachyonic degree of freedom that make the tension dynamic. And this dynamics is captured by this source term. And if we choose these parameters correctly, then you get a stable gravastar-like object, this black shell, which furthermore in a dynamic way can absorb matter and relax out to a new stable radius. And this works out numerically. Then, of course, we don't really know where all of these things are coming from, apart from my heuristic arguments about these three different components. But this source term and why it should be what it is, this is, of course, something that we cannot say. We only say that there is a possibility, there is a window here, which is such that this could actually work. So you would have to go back and think hard about whether string theory for some reason would provide this. Okay, now encouraged by this, you could also move on and see whether something interesting appears if you consider a more realistic model, such as a rotating shell. What happens if you try to do all of these things for a rotating black hole? Unfortunately,
may I ask another question before you go on?
Sure.
So, does your object have a photon ring, a light sphere? Is it?
Absolutely, because the metric is the same all the way down to 9/8 times the Schwarzschild radius. The photon ring is way outside of that.
Well, it's Schwarzschild is 3 and the Buchner bound is 2.25. But you have additional matter, don't you?
The only thing that we have, I mean, up to whether these thermal fluctuations would give anything, up to that there is no difference because everything is attached to the shell. So in the way that we have been looking at it, whether that might be an approximation, which is not good enough for various reasons, I mean, the metric is the same all the way down to the shell. And then it's ADS on the inside. So you would not, for the Schwarzschild black hole, you would not see any difference in the metric until you reach the Buchner radius and hit the shell. It's different for the rotating black hole, though. There you will see a difference in the metric. And that's what I'm coming to now. Because in the rotating case, the Kerr metric is a unique metric only if there is a horizon, of course. If there is no horizon, then you can have lots of different metrics which of course are compatible with the symmetry, the cylindric symmetry of this rotating object. And you can imagine various corrections to the metric. And in fact, that means that you would expect typically, if there is no horizon, a deviation from one very important prediction from the Kerr metric in the presence of a horizon, that is the quadrupole moment. So a rotating black shell would have a different quadrupole moment, and thus that could be an observational signature. Okay, so now we enter into how to determine what the metric actually is, and it will not be the Kerr metric. And it's quite complicated to do this. We think that we have solved the problem. So we need to have an ansatz which is a generalization of the Kerr metric. So we have used like it's like the Thorne, what's it called? Yeah, there's a couple of different metrics which you can work with, and we had to look into the literature of general relativity, and we have to do some work on our own, and we found a set of metrics that is generalizing the curve metric, and you see it here, the explicit ones that we used, and there are two parameters, Q and P, which are parameterizing the deviation from the curve metric. And it's a highly non-trivial result that this can be used to solve the junction conditions across the rotating shell. Now, on the inside, we're supposed to have an ADS metric. And we now make a physically, which we think reasonable assumption. It's not a unique one, and you can work with more general cases, but we assume that the metric on the inside is a freshly nucleated bubble of pure ADS, not a rotating ADS, but a pure ADS, which we then match onto the outside metric using a deformed sphere, as you see here.
So just for clarity, the previous metric was a solution to the vacuum Einstein equations in the exterior region?
Absolutely.
Wow. Okay. Wow.
Absolutely. Okay. So they appear in some in the literature here and there, and they have fancy names, some of them. So then we are assuming then that we have a pure ADS on the inside. And then if you're sitting there, then you would, of course, see how the outside universe was rotating around you. And the ADS is then glued to this frame dragged space-time just outside of the shell. Now, there are lots of details here, and I will just tell you what happens. And then if you want, you can go to the papers and see whether you agree. But this actually fixes at least one of the constants, is Q, and then you get a further relation. Next step is that you assume that all the matter components on the shell. So you look at the junction conditions, and then you require that the junction condition can be solved by a perfect fluid, or a sum of perfect fluids, which again is a perfect fluid. And if you do that, then remarkably, you get a unique answer for what P and Q should be in order for the junction conditions to be solved. So first we need to solve the first junction conditions. The metric has to be matched so that you get the same induced metric from the inside and the outside. That was the first one, first condition. But now the second junction condition tells you that you also have to have the energy density, and the pressure needs to match the difference in the extrinsic curvature. And there, if you demand perfect fluid, you get non-trivial constraints, which even actually fixes under assumptions that we have P and Q. And with P and Q fixed, you can calculate the multiple moments of this object, and you find a deviation from the curve metric as to the prediction of the quadrupole moment. So we are saying that a rotating black shell, which is satisfying the junction conditions by being a perfect fluid, yields a different quadrupole moment than the curve, which is actually about 7.5% lower than the prediction from the curve. In our first paper, we got a different value, but that is because we had different heuristic choices. But in the paper that we wrote now last fall, we have used this assumption of pure ADS on the inside, and then we find this prediction. Okay, now you can try to move even more, one step further, because now we said that this is a perfect fluid, but it's supposed to be a perfect fluid, which is a sum of various components. You have the tension of the shell, you have the gas or radiation, and you also have the subleading stiff gas. Let's ignore well, you can look at them here. Here you have the three components. Actually, as it turns out, and this is a non-trivial consequence of the construction, is that the stiff gas is actually as a total conserved. So the combinations of the extrinsic curvature that yields the induced energy momentum tensor is such that it's covariantly conserved. So if you add what you see here on the slide in front of you, you will get a 0. But each individual of these covariant derivatives of the various components is non-zero. And that's for a simple reason. The whole thing is rotating, and there are forces, centrifugal forces, that will push things in various directions on the shell. So we need external forces to stay put, or not even external forces. Well, external forces with respect to each of the components, but they could support themselves if there are internal forces between the matter component corresponding to the dynamic tension, the matter component corresponding to the radiation. If they're pushing on each other, the system could stay put. We already had such a component, such an ingredient. That was the source term, that in the sense, in the case of the short-chilled black hole, was transferring energy between the various components. Now, instead of energy, which is the time component of J, now we look at the space component of J, which will correspond to a force. So let us now use the same J, but assume that it also has a spatial component, but we use the same components alpha and beta, the same coefficients alpha and beta. And then we see that what condition on alpha and beta do we get if the system should remain stable, or at least at a static point, even if it's rotating. Then it turns out that, quite remarkably, you can find such a solution. And this is an amusing coincidence, maybe, or maybe there's some message here, that even though we went through all of these extremely complicated calculations, we ended up just at the boundary of stability that we had in the analysis here. So here we had a bound on alpha and beta. We had a certain requirement for it to hit the Buchdahl radius, but there was also a requirement on alpha and beta for it to be stable. Now we went through a very different calculation for a rotating shell, and we ended up just at the boundary of stability. Now, maybe it would have been better if we had been well within the region of stability. On the other hand, it would have been a catastrophe if we were on the outside. Now we're just at the boundary, which is a very strange coincidence, which we do not understand. But somehow, given the complexity of the calculations that we went through, we sort of believe that there should be some kind of a message here in one or the other direction. Okay, finally, I will soon finish. We have also been looking at early on charge shells. And here I will just tell you an amusing point, and that is that if you look at the charge shell, and then you go through exactly the same kind of reasoning, then you see that as you go towards extremality, then you see how the radius actually approaches the radius of the horizon. And the extremal charged shell actually have a radius which coincides with the horizon. So there the shell is actually approaching the horizon. Amusingly, you can now also sort of understand how an extremal black hole with a non-zero horizon size, but with a zero temperature, can carry entropy. Because you see that here that in our calculation, we find that you have a finite temperature gas on the horizon, which can carry entropy, but the redshifted temperature is of course zero. So there is it's a kind of a fight between blue shift and surface gravity, which yields locally a finite temperature, not an infinite temperature as in the Schwarzschild case, by a finite temperature with it redshifted to zero. But locally, you could say that you have a finite temperature and you have a finite entropy, and that entropy corresponds to the entropy of this extremal black hole, even though it has a zero temperature when you look from afar. Last thing, this is very, very briefly, and this is work in progress that should be ready soon. We have been trying to look at more realistic or more technically precise constructions of shells, in particular in a type 2b setting within in KKLT, where you can construct, as we have discovered then, supercharged shells, where charge is greater than the mass, and you can actually see that they are fully stable, but without any need of any energy transfer. So this is an amusing object in itself, and I will not have any time to talk about it now, but there should be a paper soon, which in a sense shows that you can find shells, stable shells, within string theory, even though these shells do not correspond to black holes. In some sense, they correspond to objects which are even more weird because they have charge greater than the mass. But of course, there is no naked singularity because everything is cut off by the shell. But the good thing is that they are stable without the need of any energy transfer. And you can see that when you bring the charge down towards the mass, then you see how you necessarily get into the situation which I've been discussing in this talk, which corresponds to real black holes. But this was just sort of a very quick appetizer in some sense. Finally, conclusions, outlook. What to do if you want to sort of make any use of this? Well, if you're interested in phenomenology, well, then clearly you should push the calculations concerning the rotating black holes. As you see, we had rather simple input, and then we could deliver a concrete prediction of the deviation of the quadrupole moment. But that was for a slowly rotating black hole. You should look at a fast rotating black hole to have something which is more phenomenologically interesting and see whether you get what kind of modification of the quadrupole moment that you get. You should, of course, try to see whether you can find a first principle stringy embedding of this. That means that you need to understand what about the tension, the tachyonic change in the tension, can it make sense? And this, of course, connects to whether it's possible to, in any way, understand whether it's physically possible to have this needed energy transfer, which is absolutely needed in order to get a stable object which can respond to perturbations in the correct way. Now, what I think might make this model unique in a sense is that, of course, there are many ideas about how to find something which replaces a black hole. And you can argue whether it makes conceptual or mathematical sense or not. And that is something that you certainly can. You can also criticize this model in that sense. Does it really make sense to have this energy transfer? I mean, all of these heuristic arguments, I mean, what are they worth? But something which seems to be, I think, a bit special with this model is that it actually can be used for numerical calculations. It's sufficiently well defined so that you can put it into a computer and you can actually start to smash it and bounce it and try to do things actually with it, and it responds and you can see what happens. As for these shells which are thrown into it and it starts to react to that, and then it re-expands and you find a new stable object. And we have also been doing other more numerically involved modeling of this, which you can find in the paper with Pretorius and Lehner. And that's something that might make this kind of object especially interesting. Okay, thank you.
Great. Thanks, Ulf. We already have quite a lot of questions, but maybe there's more more people with questions.
I had one. I was wondering just what about the dynamics inside the ADS3? Is there anything going on there that's interesting? Is the ADS3 growing, or is the stuff falling into it?
Yeah, I mean, that's a very good question. And in our paper, we were actually looking a little bit into that. I mean, an easy way out would be to say that no, everything is just absorbed by the shell. It's really absorbing everything, and nothing can get inside. But that, of course, you could imagine that not quite everything is absorbed. Something is going inside, and if that is happening, I mean, you could imagine some kind of eco effects or so on. Something is happening there. Maybe you could even imagine that parts of the energy is actually stored inside of the ADS instead. So I mean, it depends. I mean, you could really think of that, but the sort of the simplest assumption would be to say that no, everything is sort of just captured by the brain and nothing goes in.
And the piece of ADS is always a finite. Is it always a finite volume piece of ADS or is it growing or is it shrinking?
Well, I mean, if this shell is absorbing matter, then it will grow. But of course, during an absorption, if you hit it, then it shrinks, as you saw in this numerical thing here. Then it shrinks a bit, and then it re-expands to the new stable radius. But as you see, I mean, this is, in a sense, this is a terribly scaring object, right? Because what you have inside is this true ADS vacuum that eventually will consume all of the universe. And this is the first sort of tiny embryo of that, which has been induced by collapsing matter. But luckily, matter is able to contain it in the sense that it's sitting on the shell and then providing an equation of state so that this bubble is just sitting there. But of course, eventually, I mean, it grows where it collects more matter, and if you wait long enough, there will be a spontaneously nucleated ADS bubble somewhere that will destroy the whole universe.
So again, the key reason why, so normally if I try to build a shell in ADS, I mean, I put some shell, I put some ADS, I put some boundary conditions, so on. This is always top of the hill. So the key mechanism
absolutely, yes. So it's just like
have to avoid this. So normally here, if I had been top of the hill, I hit it with an incoming shell, it just collapses, or like I hit it, and But what's assuring the fact that it's not top of the hill, but it's actually metastable, is actually the transfer between the
absolutely. Without that, you cannot.
So if I think about some D3 anti-D3 gas inside an NS5. How can I think about this transfer? So I have some D3 and the D3 which come hit each other, some temperature, they hit each other and they annihilate and so on and so forth.
Yeah. No, it's a very good question. The only thing I can say is that if we add a source term, just like this, and now I'm focusing on the gas and the tension, a source term which can react to temperature, can react to the change of area, and the coefficients are like this, then I can get stability. I don't know why I should have these coefficients. I don't know whether they make physical sense, but at least you can construct, I think you can construct really local dynamics on the shell, which is such that it yields stability. Of course, there's one caveat here, because I should say that here with these values, you have to have a small perturbation. So if you throw in a shell which has sufficiently small mass compared to what you start with, then you can get this stability. If I were to throw in a shell which had too much matter, no, well, that's the thing here. If it's too much matter, then this mechanism will not work. But then there has to be tunneling, because you see that if you don't have anything from the beginning, and just the shell which is coming in, then I've been telling you that there will be a spontaneous nucleation due to that it's so entropically favorable to have a shell compared to not having a shell, that it will capture the mass. If you then already have a black shell and throw in a shell which have just a few percentages of the mass of the shell that you have to start with, then this mechanism can assure stability. If the extra matter that you throw in is too much, then there has to be a tunneling event where the shell is tunneling to a bigger radius containing more of the matter of the thing which is coming in.
Fair enough.
So
fair
then
enough.
it's a quantum phenomena, but small corrections, then it can survive
But
using
that's
this.
exactly what that's
Yeah.
exactly how it happens to fastballs. You know, when you have a fastball, when you basically have a lot of entropy, and then you tunnel into bigger configurations. So
Sorry, but
Yes,
Yeah.
but here you see also that indeed the tunneling, but here you also see that for small perturbations, then there's a classical way for the system to survive and actually slowly grow. And it's tunneling only if you throw in
yes, so
much more mass than you have to this.
So the question is, as a string theory
sorry,
method.
Josef,
Oh, sorry.
there's a raised hand for a long
Okay,
time. and
okay.
we're
Sorry, Stam.
going
Go
over.
ahead.
Yeah.
Go ahead. I'll ask afterward.
Hello. Hi, can you hear me?
Yes, please.
Yeah, sure.
Yes.
Okay. Hi. Thanks. Very nice. Thanks. This is a wonderful talk. I'd like to ask the following question regarding the approach to extremality for Eisen and Nordstrom. Because I was just wondering whether the shell that describes this energy transfer and therefore this result defines this temperature, this effective temperature in a sense, whether in this case the shell can be understood as describing the as resolving the black hole microstates.
What do you mean by resolving?
Well, in the same way that when you approach extremality, I was just wondering whether this shell that you've sort of put in by hand, right?
Yes.
Whether the constituents of this shell could be understood as describing the black hole microstates of the Schreier.
Okay, yes, that could very well be that. In fact, if I am away from extremality, then I would say that I have an object which is really microscopically different from a black hole in the sense that it will have a different temperature, it will have different entropy, even though it looks very much like a black hole, it will be slightly different. What you're saying now is that maybe if I take the limit of extremality, I will get something which is actually identical to what you would expect from an extreme of black hole. Yeah, that could be. That could.
And therefore, I would see that if I could do some sort of a resolution of the shell itself, whether I would actually be able to say that these are microstates and that and in fact, as you mentioned, the fact that it's an ideal fluid is in a sense consistent with this picture because these are all BPS microstates,
Yeah.
They don't interact, and therefore one would expect this to be an ideal fluid. So this is a sort of consistent with this picture. But
yeah, no, I think so. And this is actually part of the reason why we also looked at and took this limit, but we have not explored that further. But I think you're right. I mean, to look at that limit, you could probably learn a lot more about these components. You might get some kind of check for the consistency of the idea and get some clue on how to actually then another way of understanding also how to go away from the limit, maybe. Absolutely. Maybe you could start to see, I mean, that would of course be very optimistic, but the hope would then be whether you could start to see a little bit of this structure which is needed for stability to energy transfer or whatever. That could be a solid starting point. No, that's a very good point. Yeah.
And another question, and if I could just go on for the supercharged case.
Yes.
I remember there was, I was wondering whether it's possible to understand the paper that Atish Doublecar wrote some years ago about where that it was possible to have a black hole that had a horizon of 0 area classically, but then stringy corrections could make it have in fact a finite area. And I was just wondering whether the mechanism that sort of stabilizes the supercharged black hole, whether in your scenario could be related to what Atish had worked on a couple of years ago.
Okay, I'll have to look at that. That's some it sounds interesting.
I don't think
will
so,
have to
but
look
okay. My feeling is that no, but okay, sorry. I cannot.
Why? Oh, why not?
Because Atish has a 2-charge system which has 8 supersymmetries. So it's basically, so his corrections are based on like very supersymmetric, a lot of supersymmetry, and there's a small corrections on a tiny horizon. While here, I think it's a different. I think the physics is very different. When basically Wolf has a gas of branes and anti-branes. Supersymmetry is broken. The system has a temperature. There's a lot of entropy. So I think it's a different. I think here. I mean, if you use Atish's language, I think there'll be a small horizon around this shell actually.
Mm-hmm.
More. I mean, this shell, because it has temperature, because it has all these degrees of freedom on it. I think Atish would characterize this shell as a small horizon. He'll say that this is like a small black hole, circular.
Sure, but
I think that would be.
I would say that this would mean that if I have a supercharged black hole, I would say that fine, it was going to relax to a small black hole. If in this way, if this scenario is realized.
Yeah. But I think it's also a matter of codimension. So the main problem is, in order for this double car story to work, you need to have a black hole which is a point in 4 dimensions. So all the harmonic functions go like 1 over r, and then you have some corrections. Yeah. In Ulf's situation, Ulf's shell is codimension 1. So basically, his harmonic functions go like r next to the shell, and then only far away they go like 1 over r. So whatever, if you have to do the gravity solution of this shell, it will go locally like r, it will start growing, and then far away it will go down like 1 over r. So I think it's a different. So I don't think Atish is. I mean, in order for these double cross corrections to give you any physics, you need to have very special harmonic functions. And I think here, just because everything is puffed up in an S2, I think everything is going to be washed out. That's
sorry. So maybe this is a good point to. Well, okay, I mean, you can of course just discuss more, but we only have 15 minutes until the next talk, so to give people some time to take a little break or grab a coffee.